Okay, so now exciting time. For this next session, Rob will introduce a case control system theme, and we can get some hands-on experience first time. Maybe some of you have experience, but many of you, I suppose, will run E3SM first time. Okay, Rob is leading the infrastructure, data, and performance group in E3SM project. So, yeah.
Yes. All right, hi. Yeah, my name is Rob Jacob. I'm part of my national lab. I'm a climate scientist. I've been working on developing global climate models since grad school, really. So very long time, because it's a very challenging and rewarding subfield within climate science. So this is the hands-on portion of the tutorial. So you should all have, hopefully by now, logged on to Perlmutter, and you have a copy of the E3SM source code. And what we're going to show you how to do is how to build and configure some cases. But I'm going to start with going over the way that we control E3SM, which is through some software called the case control system, which is part of SEAM, which is the Common Infrastructure for Modeling the Earth. Now, SEAM has basically the case control system rather has, so E3SM is this giant pile of Fortran at C, right? And it's tremendously complicated. And what we've done is we've created this system of really Python scripts to make it easier for you to configure the case that you want, build the source code so that the executable will do what you want, and then submit it to a machine. So this case control system has kind of, I'm not going to go deep into the case control system. That's a whole other bucket of source code, but it basically has three things in it. It has XML files, which define the model combinations that are possible, and also it defines aspects of the machine. So when we say Perlmutter is a supported machine, what that really means is that Perlmutter has been described in these XML files. We've defined it as a machine. We've described what kind of compilers and MPI libraries are available, and what modules you have to invoke to get them, and then how to submit a job. That's all been defined in some XML files. And then the other thing the case control system gives you is then Python scripts, which will interpret your commands and those XML files to do these incredibly complicated things like building the executable in just like 4 commands. That's all you're going to need to know. And then there's also some testing utilities like Noel mentioned create test. That's part of the case control system for testing the model in various configurations. So the link to this page is on the tutorial under my section, if you're looking for it. And this is the SEAM case control system documentation. And so let's look at some key terms and concepts. Some of these you've already heard, some of these you may know pretty well. But some of the key terms and concepts, first is a component. So a component is, it's typically a climate model like EAM or MPAS Ocean, but it could also be, you've heard mention of data models. Those are things that to the coupled system look like a real model, but they're not. They're just reading in files and passing it on to the system. And so SEAM expects there to be 7 components in any coupled system you compile and run: atmosphere, ocean, sea ice, land surface, river, an ice sheet model, and an ocean wave model. Why these 7 is kind of historical. That's kind of how the system breaks down into those components. And we're actually in the process of adding another one, a economic model. So that's not totally fixed. But so SEAM expects you to build a case that has 7 of these things, and they can be a mix of these different component types. They could be an active model, like EAM, like MPAS Ocean, like ELM. It could be a data model, and those don't have fancy names. They're just called the data ocean or the data atmosphere. And then, like I said, a stub model, because something has to go in that place where it's expecting like an ice model. And then when you put all these together, put your 7 things together, you have what's called a component set. And that will define how you can, that's the definition, a very short string of how you define the case you're wanting to build. And here's an example of one. This is actually the fully coupled case. So this first string is a string about the initial conditions. So this is starting from 1850, it's a pre-industrial run. And SOI means a spun up ocean sea ice. So the atmosphere model, which is the next position, is EAM. The next position is the land model, that's ELM. Ignore what's after the percent signs here. The next position is the sea ice model, and we've defined it here as MPAS sea ice. And then the ocean, the river model is Mozart. There's a stub for the land model and a stub for the wave model. This is a typical fully coupled case. Now that's a lot to type. And it would be a pain if you had to type that every time you wanted to configure the source code to run your case. So the case control system also allows you to define a comp set alias, which is a short string to represent that big long string. So for example, all of that big long string can be summed up by this little string here, water cycle 1850. And that's going to be important because later we're going to type that on a command line. You're going to be glad you don't have to type out that whole line, whole long string. Or we're going to type out something else, but anyway. So a little note here on this page. You might have heard mention of A cases and I cases and F cases. Where does that come from? Well, it comes from these comp set aliases. And typically the first letter in that alias is a symbol for what combination of active and data models you're using. And the lettering here is, this lettering was invented, it's definitely at least 30 years old. Because it's in 30-year-old documentation for the NCAR climate model. But who actually came up with it, we don't know. But basically, probably a group of scientists at NCAR sat around one day and said, we need a shorthand way to refer to these things. So an A case is something that's all data models, pretty boring scientifically, that's just used for testing. But the B case is the fully coupled case. So that has active atmosphere, ocean, sea ice, land surface, river model, but with the stub glacier model. And then there's other things in here. The F case is very popular because that is kind of the atmosphere standalone case. So that's an active atmosphere with an active land model underneath it. But the ocean model is a data model. It's just passing SSTs to the coupled system. It also has an active river model typically. And then if you're a land model developer, you're going to run a lot of I cases. So an I cases has an active land model and an active river model, but the atmosphere model is a data model. So it's just sending fields that are read from a file to the coupled system, to the land model. And then there's other, the ocean modelers tend to run G cases a lot because there's an active ocean and a sea ice, but again, a data atmosphere, just a stub land model because they don't care about it. Maybe a data river model or maybe a stub river model.
Can I ask you a question about stub versus data? What is the difference between the two?
So the data model will read from a file. So the coupler is expecting from whatever model a certain field that it has to pass the system. Like for example, sea surface temperature has to be passed to the rest of the system. So a data ocean model will get that sea surface temperature from a file. It might be Hadley Center data or maybe data from another model and pass that into the system. A stub model doesn't send or receive data. It's just sitting there so that the compiler has something to call. Okay, so we talked about components and component sets and comp set aliases. The same thing happens with a grid. Remember, each one of these models is capable of running at multiple resolutions. Like our atmosphere model can run at 100-kilometer resolution. It can also run at a 25-kilometer resolution. And in the C++ version, it can run at a 3-kilometer resolution. Actually, the Fortran can do that too, but it's really slow. And the other models, the ocean model and the land model, they also can all run at multiple resolutions. So when you're building your case, you not only have to specify which set of models you want to use, but which resolution are each one of them running at. And so there's a grid set that corresponds to the component set, which I'm not going to illustrate. It's a similar string with underscores around it. And there's also, and almost no one ever uses grid sets. They just use the grid, which is another alias. Little string that represents a longer string, which is the resolution of each component in the same order the components appear. And then, of course, another concept in the case control system is the machine, which is just the computer that you're running on. And also, and each machine can have multiple compilers. So the compiler might be an option to the case you're building. Usually you always want to use the default compiler unless you're doing some development. Yeah.
With a grid set, can you approximate what the performance, so simulated years per day, for example, to certain configurations to approximate, if you want to go 3 kilometers across everything, you're not going to get very much out.
Right, that's right. You're
So
not,
is there a way of actually trying to approximate?
it's very hard to do in general because of how many combinations there are. What we try to do, we haven't updated this recently, but we basically have a table of typical resolution combinations and their use per day. And the best way to do it, to consult that, you can kind of interpolate between a little bit. Yeah. So when you make a choice of a comp set and a grid set and a machine and a compiler, you now have everything to put together to what the case control system refers to as a case. So this is going to be or also a base case, because probably you're going to do some custom modifications to the initial case in order to do your science. And so an out-of-the-box case is something that will configure, compile, and build right out of the source code. You're just giving it a comp set and a grid set, and you're building and running, and off you go. And you can do a lot with these basic cases. You can do all kinds of modifications to the nameless parameters without touching source code, and still do lots of interesting experiments. But the out of the box cases by themselves, probably most of the science on them has been done. Okay, so now is the time when you want to get out your keyboard. And I am actually going to. All right, so here I have, we can see this, right? Yeah. This should go away. Here is my Macintosh. I'm using iTerm 2, which is a great replacement for the default terminal that comes with Macs. I recommend it. And I've logged on to Perlmutter already. I'm in my home directory. I have a bunch of junk in my home directory, but I also have a copy of the E3SM source code. So I'm going to CD into that directory. And then the SEAM and its case control system is all included within the E3SM source code. The E3SM source code is is what we call a mono repo. It's all the source code for all the models are kept in one Git repository, except we do bring in some other pieces by what's called a Git submodule. And the SEAM case control system is one of those. So just to double check, we're in E3SM SEAM. Now we're going to go one more directory down to scripts, and I promise we're not going to go any further than that. Hang on, then you didn't see that. All right, so inside, let me clean this up a bit. Okay. So this should be what yours looks like. These are there's some directories, but there's also some scripts, and these are the kind of the first initial scripts that you would use to command the case control system to do something. And the one we're really interested in is create new case. But first, I want to show you query config. So remember how I said that E3SM and the machines it runs on and the compilers it uses are all described in XML files. Query config will help you inquire into those XML files about what it knows and spit it back to you in a handy text format. We can do query config, comp sets. How many comp sets are defined in E3SM total for all the months? Let's do all. Wow, that happened so fast you probably didn't see it, but it's a bunch. Here's all the I cases, here's a bunch of F cases, here's some data model cases, here's some fully coupled cases, just a whole bunch of these. So, and what's being output here is the comp set alias, and then the full comp set long
Can you
name.
show the full line of what you typed after query config?
There's comp sets.
Yeah.
Mhm. All of these Python commands have help strings. If you do dash dash help on any of them, you'll get more information. However, I did notice that query config is broken for one of the options. But you can do query config grids. Here's all the grids. Now, they didn't put it in the nice grid set name, but they did give you the alias and a verbal description of what each component is running on.
If anybody is not able to do what's on the screen, why don't you just raise your hand and we can come walk around and help you.
Query config dash dash machines. Here's every machine that we've defined within the source code. That's the thing, all of these configure, all these XML files that define machines and comp sets and grids are versioned with the rest of the source code. So that when you get a git hash, you know that that hash can do these comp sets on these machines. We can, I believe we can do PM CPU. Yeah. So here's a brief summary of what the case control system thinks of Perlmutter. Specifically PM CPU, which, as Noel mentioned, there's a CPU and a GPU partition of Perlmutter. We're going to just be running on the CPU partition. And there's some information about it right there. So it says there's a string here, a little bit about the machine, what the operating system is. These are the compilers that are supported. And the first one will be the default. So Intel's the default compiler. But GNU, NVIDIA, and this experimental one called AMD Clang, they're also supported. I don't know why you would ever use those unless you really want to know about Fortran things. The MPI library is mpitch, 120 processes per node, tasks per node, things like that. All right. So now, let's go back. Also, if you somehow use CESM as well as E3SM, it might get confused about what model, because both CESM and E3SM use the case control system. So when you learn these commands, you can run either model. Of course, the comp sets are a little different in the CESM land, but all the basic commands are the same. But if you get if you're somehow using both and the scene is getting confused, you want to make sure your scene model variable is set to E3SM. That probably won't be an issue for most everyone here. So anyway, let's create a case. So we're going to, and this is also on the tutorial webpage. There's a text file called tutorial commands that has all these commands in it. If you don't want to copy and paste off this webpage, or you can also just type it in. But basically, we're going to create a case with the most basic case control system command: create new case. And the arguments, and these are the three required arguments. It's the name of the case, and that can be any string. There's some rules like don't put special characters in it, things like that. But it can be anything. When we're doing a production run, a lot of thought goes into that name because it winds up being metadata that's copied everywhere. It's in the file names, it's in the metadata of the NetCDF files. So when you're doing production runs, you might want to put some thought to what this case means. And then my comp set, I'm using a comp set alias. In this case, I'm just going to run an X case. I don't know if you remember from that table of letter cases, but an X case is basically something we use just for coupling, just for testing the coupling. But I'm using here because it's really easy to build. Yeah.
Make it bigger so that the people in the back can also see it.
Is it still not big enough?
I think that's big enough. It's
Oh, this-
the web page.
The web page. Okay.
That better?
That better?
Yep. It is. Oh, right.
Okay. Okay, sorry about that. So, and then this is a resolution alias, which is no resolution that we don't even use anymore in E3SM. But let's see what that does. Oops. All right, so it output a bunch of stuff when you did that. First, it spit out what the long name is for that alias that you just did. This is a long name, it's all these X cases. What these are doing is they're kind of like stub models, or they're kind of like data models, but they just pass sine waves. So you can only use them together. You don't want to mix them with another model. Here's where it pulled out the comp set. Other stuff, which I'm not really going to go into. But basically it's telling you what you just told it to do. Here's the long grid name. The long name for the grid. So as you can see, it again is that same pattern. Here's the atmosphere grid, the land model grid, the ocean and ice grid, the river grid. The comp set again, how many tasks it's going to be running on. All kinds of useful information. Oops, I already made this. But now if you change directory, so yeah.
How do we define the different machines? Different machines for the building case.
So for a different machine, you would just do -- machine and then the string for the machine. Assuming the machine has already been defined. Big system. Now, the case control system is smart enough to tell what machine you're on. Like it'll look at the host name, or some other thing that's in the file system. So if it's a supported machine, there's also a clue to how to find out what machine. So that's why we don't need a machine argument here. We're on Perlmutter. It'll recognize that it's on Perlmutter and it'll do the right Perlmutter thing. So,
What if it's the unsupported machine?
if you do an unsupported machine, it'll try. It'll try to define things as if you're on that machine. So you won't get an error. Because there are occasions when you want to debug something and I want to pretend I'm on one machine when I'm really on another. And so I don't think, let me try that actually. I don't think you get a very good error message. Let me try.
That's just that's something I want to. Yeah. That's essentially what's stubbing something is. If you have a stub ocean.
Yeah. It happily built the case as if you were on this other machine. But once you start typing more commands, things will go wrong. That's when you want to check. Oh, yeah.
Yeah. So this is. Some things.
That's where he said.
Let's get.
So I think those, yeah, this will be like very vanilla, very easy.
All right, so we created a case. And if you go to your case, do an ls -l.
No, I'm not.
So this case directory, the case dir, is going to be in a very important place that you spend a lot of time in as you get your case just the way you want it. Because right now you have an out of the box case, right? It's directly from the source code. It's a predefined comp set and a predefined resolution, and all the input variables are all predefined. And it'll do something if it's a supported case, but it may not do anything particularly interesting. But there's all these commands, all these things have been put in this case directory that will help you get the rest of the way to starting the job. And also it provides some provenance on what exactly is in this case. So if you tar up this case directory, it has everything that happened and that was interesting or unique about this case that you made, as well as the tools to create it. So all these scripts are created in the directory. It has a case.build script, which we'll call later to actually build the model. It has the case.setup. Even though you've mostly set up your case, you've defined the comp set and you've defined the resolution, but you may want to do a few things before you build it. Case.setup will look at those and process them. Mostly build system. But mostly it's changing the processor count actually. Check input data. Noah mentioned that the case control system has some smarts in it about what input files are needed. And there's like 50 to 100 input files needed for the model as a total. You know, between what the atmosphere reads in, what the lab model reads in, there's dozens to hundreds of files. 100 files. And, but they are defined to the case control system, and the case control system will check that directory that all the input files are in to see if they're all there. And if it's not, it'll go download them from our server, which is a publicly accessible, real usable server. So if you're running a case that's never been run before on this machine, it'll go and download the files that you need, as long as it's a defined case. But by now, on Perlmutter, almost everything's been run. The PE layout command will show you what the processor layout is for this case. Preview name list. So the case control system works with the models to build all the runtime name lists that it needs for the case that you configured. And that will show you what they look like. Preview run will show you what the batch command looks like. XML change and XML query for changing some of these XML values. So I mentioned that XML is a big part of the case control system. And so also in this case directory are the XML files that describe this case, not general cases, but this case that you built.
Yeah.
And again, I'm not going to get into those because they're just XML. Readme.case is a nice piece of provenance. If you more that, it has the create new case that you command that you issued, and some other metadata about the case. But the next thing, so now we have this case, let's do case.setup. So case.setup did a few things. It created the run script that will actually be submitted to the batch system, because the case control system knows how to construct that. You don't have to build the run script yourself. It invoked the commands to build the name list for each component model that you have in this case. So every one of the component models, whether it's an actors model, a data model, or a stub model, has to have one of these Python scripts called build NML, build name list. And it will build the name list that is appropriate to the case that you defined. So all the defaults for the model that is in this case will be initially created. So if we do an ls -l, we have even more things in this directory, including a script called case st is short-term archive. I think I'll mention that later. Case status is another piece of provenance. It kind of keeps track of everything that's happened so far. So a case setup started, was successful. So every time you type one of these case commands, another line will be entered in that file to tell you what you did. But let's do now the big one. Let's build. And like Noel said, it's going to take a few. This is not going to return immediately. Yeah.
Do we usually want to like Q command on like a case build, like QCMD space / like case build?
Oh, you mean send it to the queue?
Yeah.
You could. It's okay to build on the login nodes too, because it'll parallelize kind of nicely. But if you feel like it's a little slow, then that would be a good thing to do, to go and grab a interactive node and build on an interactive node. Then you have a node all to yourself, run the build, and you're not competing with other users on the login.
Well, is there any chance we could see history or something just so we can see what the sequential steps were?
Yeah.
Or maybe that's common.
Oh, that might be in replay. Okay. So there's another file called replay.shell, which is trying to build the steps that you could replay. So first I typed create new case. I did that inside the source code directory in Seam scripts. I then CD'd to my case dir, which in this case I called it my case 2. And then I ran case.setup, and that's all I've done so far. And I showed you all the files that are in the case directory. All right, so now, like I said, it's not a lot. This case is not a lot of code. That's why it shows it So now we're gonna do case.build. So at case.build, so what's happened so far is we've defined our case, which is a long string of comp sets. Each of those comp sets corresponds to, we can go look at that actually. Back up in the E3SM top level directory. I'm in the directory called components. So, and I'm going to list this directory called data components. So here's the source code for each one of the models that E3SM has in it under this directory called components. And also in that directory is a directory called data components. And here's the source code for all the data models. So I've chosen a specific set of models for my case. And now the build system knows to go and build the source code from these directories, from the directories that correspond to each model. So this is an X case. So yeah, it's actually over here. So in that case, it's actually going to ignore all of that. And it's going to build the source code in these directories here in this comp state. But if I was building an F case, right? An F case is the data atmosphere, or rather the atmosphere standalone. It would build all the source code from here, all the source code from here. It would, and all the source code from here. It would not build the source code from the ocean because it's an F case. It would instead build the source code from here. Yeah. So what the case control system is doing is based on your comp set, it's figuring out where in the source code it needs to pull files from to build the execute. And that's why if you want to change that up, if you want to build a B case with an MPass ocean, you got to go all the way back to create new case and make a new. You can't convert an F case to a B case. Yeah, get a question back. Go ahead.
So we had a couple of commands that were case underscore something else. But now we just did case dot something else. What happened in between?
Just inconsistent naming from the kind of, this developed from some shell scripts.
Okay.
It's got a long history. We're actually, there's a project going on right now to make this all more Pythonic.
Okay.
So you'll have like seam, space, command, stuff like that. So look for this to get a little less arbitrary.
Thanks.
Yeah. All right. So that was a brief detour in what we're going to build. So now I'm going to type case.build and all of that source code, which it's a relatively small amount of source code, but it's still hundreds of files, of Fortran files, are now going to start to be compiled. So first it builds the name list. It keeps building the name list because maybe you changed something and it changed something in the source code and it wants to rebuild the name list again. But now it's going to call from each model, it's going to call a build lib command. First, it's going to build some libraries that all cases use.
Yes.
So the first thing it's going to build is the driver. It's one executable ultimately. So there's a main program that drives all the models, no matter what models are part of the system. And so that's the driver. And it's going to build the timing library that is used in every system, the time thing. Then it's going to build the IO library. That's usually the first thing that takes a while. So while that's go, this is why I wanted you to have two windows open, because now we're going to go watch what's happening while this thing is built. So I've got my other window to Perlmutter here. My case too. Now, there's not a bunch of object files and compile time, flotsam and jetsam appearing in this directory, because the case directory is supposed to be kind of neat and clean, because this is where you're doing your science, right? And getting things customized just the way you want it. So the build.
What was the name of the case? Just name it whatever.
What's that window?
That is just a string.
Nah.
Can I ask a dumb question first? All of these things and commands, are they one of the inline pages? Can we see all the command lines that you're going through?
Yeah, there's a tutorial commands text file where I put all of these. Yeah. It's on the tutorial agenda page under this section. So, okay, this thing is busy building, and when the case control, so the case control system, like I said, has a long history. And part of that history is informed by what computer systems were like back in the day. And back in the day, you had a small amount of disk for your home directory, and then some large amount of disk somewhere else for your output. And that large amount of disk for your output wasn't always stable. It would go down, it would be wiped out, stuff like that. So the build is happening over on that other file system. The machine says where it is, the machine configuration says where it is. You can find out where it is through this XML query command. XML query. It's called the XE root. And actually, I took too long to do the rest of this. The build already finished. So you'll get a nice build that's finished successfully. All your code's okay. You didn't make any mistakes. You're ready to do the next step. But I want to show you what was happening while that build was running. So if you do XML query, again, XML query is a command that will look at all these XML files and pull out the things that are interesting. And this big long path is where the model was built. So it's not on the home directory where my source code is. My source code directory is sitting here on global U2, but the XE root defined in the config for Perlmutter is over on scratch space, T-scratch, which is good. That's where we want. Yeah.
Is XE a specified argument, or is it like grepping through those XML files?
It's in the XML files, yeah.
Okay, so I mean, I
You
guess.
can't overwrite it.
XE need to be predefined, like, are there a set combination of things that you search for any arbitrary string? Is XML query searching for an arbitrary string, or is XE predefined?
So it's one specific string.
Okay.
Yeah. So it's built. So it's built from some pieces like T-scratch SDR, RL Jacob. There's an environment variable on Perlmutter called like T-scratch or something like that, which is defined per user. So it gets it from there.
Okay.
Like yours will be T-scratch SD, maybe some other letter, your username.
Sorry, I'm the argument to XE to the XML query command.
Yeah.
Can that be any?
No, it has to be an XML variable. Sorry, it's not there. Yeah, sorry.
That's fine.
Sorry. And I can use XML query to do fun things like, well, I don't want to type that whole nasty thing. So here I'm going to do XML query minus value XE root. Is that right? Yeah. And notice I put backticks on the other side of this. So what that'll do is that'll take this string and put it on CD here as the argument. And now I've gone to this XE root directory. And what's in this XE root directory? How am I doing on time, by the way? So what's in this XE root directory is a lot of, there's a directory for all the object files that are going to be built. But the one file you want to pay attention to is this one, .build log. Basically, all of the output from the compiler for the source code of the main model will be in that one log file. Since we switch to C, it all appears there. So if you've ever watched code compile, and when it finishes correctly, it hopefully cards it up so it doesn't take up a lot of space. But if you've ever seen if you've ever watched something compile, you might know what this looks like. It's a whole bunch of output from compilers, compiling commands. And if you had a build error, you would probably look there. All right. So also in this directory is a case root, because you might get lost CDing around all these directories. So there's a case root to tell you where you came from.
So probably has equals. Yeah.
Right. So now the model has been, we've configured our case, we did our setup, we built the executable. Did I show you what the executable was? The executable was right here, E3SM.exe and then a string, in case you want to build it again. Yeah. Here's the executable right here, and here's a copy of it. If you rebuild it, it'll make another copy of it, so you keep accumulating executables as you keep rebuilding it. In case you want to go back and find it again. Where does case case root is defined by the machine you're on. And you can get it from your case directory, that XML query.
Did I have that file? Did I have that file?
It should be, if you go back to your case directory and you type, the command was XML query case root. It'll spit it out. This was defined in these XML files when you created the case on this machine.
You have a file named case.
No, this is an XML variable of case root.
Oh.
And this command is looking it up.
How did you more it?
Yeah.
How did you more case?
Right, what?
More case.
Oh, that's just the output from XML query.
Like the third line from the top. Yeah, he does.
Oh, that, in the build directory, in the exe root, it actually wrote a file. Sorry.
Oh, hey.
Because there's no XML files in the exe root.
Okay, okay, so.
All the XML files.
When we use the case, we will copy the source code into the directory.
No, you can build, that's a good question.
Still.
So a very good question was asked about the source code. When you create a case, does the source code somehow get copied to that case? No, it doesn't. The system is set up so that you can build multiple cases off the same source code. Now you can reverse that, and the run script we're going to be talking about later allows you to have a source code clone attached to each case if you want to do it that way. But another way to do it, and the way I'm showing it, is I've CD'd into the scripts directory for one checkout, and from this directory, I can go back and create new cases as many times as I want. And as long as I have a different case name, so a different directory, I can just keep building cases off the same source code.
Okay, so.
Yeah.
Sorry, I would like to change the source code. Change part of that. How should I do that?
Okay, so if you then want to edit the source code, so
Okay, so we are.
because my copy of create new case is inside this copy of the case control system, inside this copy of E3SM, any of the other source code I edit in this file, in this directory, will get built by and accessed by that create new case that I call here. So it's gonna hop back up to E3SM and grab the source code. If I just do ls ... components, it's in the same, so the version of Seam inside this version of E3SM will grab all the source code from that version of E3SM when it's configuring a building. So if you edit anything, if you edit something inside the atmosphere and you build an estimate, it's going to use your atmosphere. That atmosphere is built in.
I'm trying to answer questions on Slack if you want to ask me something there.
Can someone remind me how long this session goes to? Half past? Okay.
Have a break at half past, I think.
All right.
2:30.
I thought that was what, not the agenda.
All right. Well, then we're almost at the end here anyway, so let's do case submit. So large computer systems like Perlmutter and Frontier, a few years ago, they had a whole zoo of software to submit cases. Some were using Slurm, some were using B sub, some were using PBS Pro. Lately, they've kind of all settled on Slurm, but anyway, it was a mess to try to remember how exactly do I build a case and build a batch system and submit a job. So the case control system came along and said, you just got to know one command, case submit. And whatever, if the machine is defined to the case control system, case submit will do everything necessary to submit it to the queue. So if you've built everything, we can submit the job.
So we're doing.
So it's going to build the name list one more time.
So you transfer.
Submitted the job called case run. This is the command that executed. The job ID. We can now use SQ command. I'm going to use my username. SQ, whoops. Oh, mine is U, sorry. So there's my job sitting in the. Oh, I forgot something. Hang on. I'm now gonna S cancel that job. I forgot, this command is also inside that file. So right now, during this tutorial, we have a special reservation form. It's active now, and it'll end, I don't know, in 20, 30 minutes or something like that. But basically, they put aside 50 minutes of Perlmutter just for us to submit our job. But we have to add some special arguments. Normally, you just type case submit with no arguments like I did. But this is a lot to type, but it's in that tutorial commands.txt file. It's on the agenda. It's in the Slack. Basically, this is going to tell it to put it on this account, put it in this reservation. So it'll, because there's hundreds of people waiting to use all the nodes on Perlmutter. We're going to jump ahead of them. Yeah.
So is this like just specifying a project essentially? Like,
So if you already submitted a job, don't worry about it. You can submit it again.
He's not getting dash dash. Seems like people in.
All right.
You really have an issue?
Right now, my job is already running. This little R under the ST here says it's already running. Let's see who else is running in our reservation.
Oh, still.
Oh, wow, look at us go. Everybody running under our account. I did SQ by a day, our account name. I'm gonna find your username here. The job name is automatically run dot. If it's PD, it's finished. If it's PD, it's waiting. R is running.
yeah.
You can go back to your case directory, look at the case status file. At the end, it'll say knowledge starting.
And then.
Or finished. Oops. Yep, still running. Oh, no, it's still running. What's it doing while it's running? Would you like to know? It's doing something, but that something is often another directory to keep your case directory clean.
Good.
That directory
Everyone having a grand.
is the rundir. So I'm going to go to the rundir. Oops. All right. No, it just finished. So in the run directory, we have lots of runtime logs that are being written to. And again, I didn't get here fast enough, the job already finished. If you look at this run directory, while it's running, you'll see these log files filling up with information. And they will, depending on how fast each component is running, they'll spit out different things, and they'll one will be more recently written than the other every time you look at the command. This command that I'm using, Unix says list minus L full detail minus T by time written are reverse order. So the last thing written will be at the bottom of this command. After I output it. So while this is running, I would just do that command over and over again to watch the log file.
What's the XML variable?
Yeah, what?
What's the XML variable?
Runder, R-U-N-D-I-R, yeah. Now, we're coming to the end of my session. And what you see here is you've seen the guts of the case control system that you can use for release. So let me jump back to the case stir really quick. I don't know if this actually had any.
Yeah, I'm wondering.
Yeah. So it's just, I mean, like, one of the things that happened in the case directory, I could create a nameless file called UXarray. I can edit that file and I can put in different values for nameless variables that control the coupler. If I was running a more complicated case, like an F case, there'd be a UXarray file for the atmosphere and a UXarray for the land model. And you can edit those files right before you hit case submit. Variables. The model take the variable. And that could be things like, it was just a small. Really fine great control over various physics within the model. But if you want to set this case up again, or you want your colleague to set up the same case, they would have to repeat exactly the same commands on the same source code version. You don't get the same case. So we have developed over the years. We will execute all the commands I showed you based on some variables that you define at the top of the file, the shell script. And we're going to hear about that next and how to use it. Edit the shell script, not just one shell script, and all that stuff will happen, including maybe checking out the source code. And then you can pass that run script. It should be your professor or whatever. All right.
Yeah. I literally verbatim did,
Rob showed you the basic command how to use SIM directly. But often what we end up doing is we package those commands in a script.
Talk in the microphone for the video.
Okay. So I'll show you how to do the basic command from SIM, which is really important to understand sort of what they do. But often when we run the model, we end up sort of packaging the command in a script so that we don't have to type all of this manually. And also, if we want to share a simulation with somebody, we can give them the script and they can actually reproduce exactly what we did. If you do the SIM command on the command line, then it's harder for somebody else to reproduce exactly what we did. So for the more important simulation, we use what we call a run E3SM script that packages a lot of those SIM commands into a single script. So Wuyin has prepared a version of the script. And basically what the script does is it does what Rob went over. There is a fetch code which will actually clone and do all those steps. So you can fetch the code. So they will do a git clone and then it will do the git submodule, which you did manually before. Then it will create the new case. It may change the P layout. Sometimes we want to do P layouts that are not there by default. So there's an option in the script to do a custom, what we call custom P layout. Then it will do the setup, the build, additional runtime option. It will save the script somewhere. and then it will submit. So you can do all of this in the one script. So let's go through some of those steps. So if you look at the one script, so the one script is available. If you go from the agenda tutorial page, you can find a link to the page that Wuyin is displaying that has then a link to the one script. It's also here. Okay, so I should have started with that. Sorry about that. All right, so this is the script. So the name of the script, let me explain a little bit. So this is running V3. LR stands for lower resolution, and then this is a historical simulation. So those are the simulations that have transient forcing from 1850 to 2014. 0101 is the ensemble member. It refers to the year where we branched. And in this particular instances, Wuyin has configured to branch from year 2000. So you would basically be rerunning a historical simulation starting from year 2000. Okay, so we have create case in the script. Then we also have an option to build. Setup, okay, then setup. Inside the script, you'll see there's a number of different functions. One of them will be to set up the case, to build, and then to run. You can specify to either run a short test, which is typically what I would recommend when you get started. You run a small test just to see everything works. So those cases are specified with that variable here. So the first part, so the string is separated in underscore. So you have 3 sections here. The first section is what we call the P layout. So you can put a default P layout, which could be XS for extra small, small, S for small, medium, large, or you can do a custom one where you say, I just want to run on 2 nodes. So what Wuyin has done here, he has specified he just wants to run on 2 nodes. So that will use that custom function in the one script. And then the second part of the string is how many runs you want to do. So this is 1 times 1. And then the third portion is the length of the run. So this would run 1 times 1 day, just to test that there's everything works before you submit a long run. There's nothing more frustrating than submitting a 20-year simulation on a Friday afternoon and come back on Monday morning realizing that it crashed within the first 5 minutes. So I highly recommend that you do a short test before you submit your long simulation. And sometimes we like to do also make sure that it restarts properly. So sometimes we'll do 2 times 1 day or 2 times 5 days or things like this. This is where you specify in that variable called one in the one script. And you have some example there what other options might be. And then inside the script, there is also, it will directly submit the run if you ask it to do that, and it will submit that with the, in this case, it was modified to use the reservation. So if you go back maybe to the, let's look at, so within the run script, there's a number of logical variables that you can turn on and off to decide what you want to do. Yes, so if you look for toggle in the run script, there's a do fetch code can be true or false. So if you have not cloned, this will decide whether you clone the source code or not. So typically the first time you'll have do fetch code equal true, but if the code is already available, you set that to false and it will not fetch the code again. Then the do create new case typically will be true. And then do setup will typically be true. And then there should be a do build somewhere here. Do, I see bigger letter, I was confused. Do case build will compile the code, and then do submit will submit. So you can, if you want to only do some of the steps that were mentioned, you can turn on and off some of those cases, some of those logical flags. So tomorrow Wuyin will go into much more details about how to use the script. But if you'd like to just try it out, you can what we recommend is you create a subdirectory like Wuyin is pointing here to, and then you copy the script into your directory. And you can actually, this is predefined, so it should just run. No? You copy the script in your directory, you can run it and it should work. That's it. It should.
You can manually select or just click this one copy and then paste to your terminal. Then you see that response on your screen if you run it command.
It has the right reservation.
Yes, it has the right reservation for today. Wuyin customized it for today. So this is what we do often when we actually run simulation, because we want to know what we did. So Wuyin may start a simulation for a particular ensemble member. I may want to redo it for a different ensemble member. So he will point me to his script and I will modify it. And then we also archive those scripts so they're available in the future if somebody wants to reproduce them.
Okay, so for those of you running the sample X case, you can tell that it was successful by watching the queue, but also in the case status file, you'll see this case run.success command. When that happened, you know, the date and time and the job number.
What was that? Was that command again? Case status?
Case status. That's a file inside the case directory that keeps track of all of your setup build.
Yeah, and for the new run, we just went through. So if you open a second terminal, they can enter into this directory. You see the new case structure, just like the same structure Rob just showed.
When you use the script, somewhere there's still a case directory with all those files, and there's a run directory and an exe root directory. You can still look at all the things I showed you to watch more carefully about what you're doing. You can even, after you set up a case with the script, you can go and edit stuff in the case directory directly if you want to. What was the other thing I was going to tell you? Oh yeah, so like I said, we have this reservation, and once the reservation ends, your jobs will be back in the regular queue competing with other users. But if you the run script job is going to run one day. We did an out of the box case with the X case. Out of the box cases by default run for 5 days. Because that just seemed like a good number. So, but if you try to run a more complicated case for 5 days, you're going to be really disappointed by the output, because most of them are set up to only output stuff monthly. So if you want to try a case that does something more interesting, I put in the tutorial commands file, this is something to try later, I put the commands for building an F case, and then a couple of XML change commands that'll make it run longer. So instead of for 5 days, it'll run for 3 months. And if that runs successfully, when you go to the rundir, you'll see history files from the atmosphere model, from the land model, from the river model. It'll have H in their name and they'll end in .nc. We're going to go more over analyzing output later. But that is something for you guys, homework for you to think of.
Yeah, definitely before departure, maybe, so we can save some notes for the post-processing. Now we will have our first post-processing session. For this session, we will practice on existing data. Maybe later on when you have longer simulation, you can use your own simulation data. So in this session, firstly, we will have Paul back to the stage to talk about the graphical tool NcVis, which is you developed it, right? So for visualizing data on unstructured grids. And Charlie will be next up to talk about NCO, the NetCDF operator, to manipulate climate data sets. And then Tom will present the Python approach to do the similar practice. Okay, let's welcome all.
Thank you, thank you. It may have snuck through earlier, but by training, I'm actually a C++ developer. So I went to University of Waterloo and had 2 years of industrial experience actually doing C++. So my main contribution to the field of climate science is not so much science, but just, you know, showing off my relatively good coding skills. And so I primarily use that to do tool development. So if you actually check out my webpage, climate.ucdavis.edu, you can check out some of the other tools as well that I've worked on. Tempest Extremes, you may have heard of. It's kind of a fairly popular package for doing feature tracking. And Tempest Remap, which is used for regridding data between different grids. But today I'm going to talk about NcVis, which is a tool that is still under development, I would say, still in beta mode. So don't be surprised if it seg faults on you for whatever reason. But I think that it's pretty useful for visualizing unstructured data. It's one of the few tools out there that allow you to basically do a quick look at unstructured grid data. For today's purposes, you can access NcVis through my directory, which is /PAULLRIC/NcVis/NcVis. But you can also install it via Conda. So there's a Conda package called NcVis-climate that you can actually install locally for your use. And so that's probably the best way to do it, or again, just using the install that's already available in my path. It's also available through the E3SM Unified environment. So when you load E3SM Unified to do builds, to do E3SM on Perlmutter, you can actually access this NcVis tool. And so many of you are probably familiar with NCView, which was developed by Dave Pierce years ago as kind of a quick look tool for looking at xCDAT data. One of the shortcomings of NCView is that it doesn't support unstructured grid data natively. And so our goal here was to allow us to look at that unstructured data, again, emphasizing that all of this data that is being output by E3SM is kind of this one-dimensional spatial form. And so it's kind of hard to visualize unless you have the right tools. We've been pushing hard in the past couple of years in order to kind of come up with a new tool set that makes it basically invisible to users, that any unstructured work is going on behind the scenes. But again, that's still something we're advancing on, and we look forward to any feedback that you might have on this matter. Wherever you find that there's bottlenecks or issues or difficulties in dealing with some of this data, please let me know. So the path that we're going to be working on is given here. This is where we have basically some example data that was generated previously through E3SM that comes in a variety of different history files. So here we've got H6s, H5s, all the way up to H1s. And so that's basically just different streams with different variables that are output by E3SM. The environment that I'm using here in order to do this visualization is NoMachine, and I strongly recommend using NoMachine if you are working through the terminal on Perlmutter. You can find out instruction. Well, basically you Google NoMachine to download the software, and then you can go NoMachine NERSC on Google in order to get NERSC's specific instructions on how to install it for accessing Perlmutter. And it allows you to access Perlmutter through a GUI, basically, as if you actually had a computer that was plugged directly into that supercomputing system. So this is the GUI that I have that is floating on NERSC, but if you don't have that, you can also use X11 forwarding. In that case, if you're on a Mac, you want to have X ports installed, and if you're on Windows, you want to have X11, or there's another X something or other that's available for Windows that you can use as well. All right.
Really, security just told my server is not
Not secure enough. Well, I can't fix that. Call up Noel. Okay, so I'm going to visualize, I'm going to pull up NcVis here and visualize this .h1 file. Okay, so what you do for NcVis is you basically just put the file, you put NcVis and then you put the file name that you want to visualize. That NC file, netcdf file, needs to have the lon and lat variables inside of it. Otherwise, NcVis won't know where exactly to put all the data points. And so it uses some cool algorithm in order to basically build the two-dimensional visualization from this point cloud, basically from this set of random coordinates that are output through E3SM. Okay, so let's say I want to look at temperature, then I just pick which variable I want. In this case, T corresponds to temperature. Temperature has a time dimension, a level dimension, and ncol. Remember, ncol here corresponds to the horizontal coordinate or the column number that you're in. And then down here, range, this states basically the range of values that are plotted So you'll notice on the legend here, it goes, the numbers at the top of the legend and the bottom of the legend match exactly with the range values here. Here I'm using a thermal heat map in order to do the visualization. Let me just make that a little bit bigger. Okay, so you're probably wondering, well, what is this? Well, remember how I told you that vertical levels in E3SM go from the top of the model to the bottom of the model. So this is really close to the top of the model, and you can see it right here in LEV. We're really at like 0.1 hectopascals, which is really, really high up in the atmosphere. So I'm going to go backwards here to the largest value of LEV, which is of course the one near the surface. And this is now washed out because temperatures here are much warmer than they were at the top of the atmosphere. And so I can click reset here for it to regenerate basically that interval. And you can start to make out the continents now. If you want to align yourself as well, you can click on the overlays section here and click on, say, overlays coastlines, and then that will pop up a it'll draw the shape file corresponding to these overlays on top of the map. And so now you can very clearly see the Himalayas, the Andes, and other areas where there's different temperature variations in here. Okay, so let's say I want to step through this data in time. I can just use this plus. Here, the data is output on a daily basis. So you'll notice down here, it tells me which day is currently being visualized. So this is 2014, January 26th, 27th, 28th, 29th, 30th, et cetera, or I can press play and that'll automatically basically play through that using via animation. All right. If I want to go back to the beginning, I click reset and it sets me back to 0. All right. If you want to change the visualization, say you want to emphasize the low values, you can click here, that changes it to low. You can emphasize the high values, change it to high, etc. If you want to flip around the color table, you can click this up and down arrow, that flips around the color table. If you want to change the color table, you can go here. We got a few different options built in. Let's say we want to use a blue-red color table for whatever reason, and then it looks like that, and then we can play it from there. Okay. You'll notice that there's a lot of artifacts being produced here. It's kind of chunky in some regions, and that's a product of the fact that it's using the fastest possible mechanism in order to actually do the visualization. And so we can actually change the renderer to like a KD tree, which provides the best possible visualization. And that produces something which is generally much smoother. And we can, again, run that through and visualize. If you want to export this picture to a PNG file, you can click this export button right here. And so I'm going to do export to NcVis output.png, or you want to put in your own home directory for that. And you can click export, and then that'll save it as a PNG file. I did that earlier here, and then you can use the display command in order to basically pull up that PNG file that you generated. This is a different one, but same basic idea. All right, so that's basically it. It's again a quick way to do quick visualization of some of this unstructured data. If you have any feedback or questions, please don't hesitate to shoot me an email. But one of the options, this is one of the options.
Okay, next we will have Charlie to talk about NCO. Charlie is professor at University of California, Irvine.
Thank you, Jill. Hi, everyone. I teach at UC Irvine, and I also, like Paul, do climate research, mostly in polar and radiation, all those contributors to the Q thermal energy forcing term on the right-hand side of the equations that he showed earlier. But I also do some software development, and it is used in E3SM for post-processing. And to put it in context, I thought what I would show in the limited time available is, so you've learned how to run the model and you've learned how to visualize the model. And unless you're a computational scientist or an artist, neither of those is doing science, right? Okay, so what you want to do in the end eventually is learn about the Earth's climate. So to do that, often we want to put what we simulate in E3SM and put it and judge it side by side against either other E3SM data, which you'll be able to do because you have all these pre-made data sets, or other model data. So that's what the CMIP6 means. That's a model MIP or intercomparison project from all over the world, or hopefully observations. And that's the aerified part of that title. So I could have called it regridding and climatologies, but the point of regridding and climatologies is to make point-by-point intercomparable values that you can subtract and compare to observations or other models and then gain scientific insight. So that's the general area that we're working in for the next 10 minutes. These group members on the infrastructure team have been very helpful in getting NCO, which stands for the NetCDF operators, installed, and Helen Hay, whom I just met for the first time at here at NERSC, has been doing that for many years. Okay. So I'll start out by pointing you to what you'll probably use after nothing works, which is the documentation. So there's good documentation. It's all publicly viewable. We're going to start with regridding, which is a way of taking the unstructured data that Paul was just visualizing and putting it on whatever grid you would like, either structured or unstructured. We're going to talk about some of the terminology, map files, grid files, and then we're going to move into climatologizing, if that's a word, data sets. So taking model output and creating seasonal means, annual means, and regridding at the same time, or splitting, so making time series, single variable time series from model output. These are all activities that are done at all modeling centers, and this will help you interoperate with other modeling centers. And then there's an optional exercise at the end that you can perform during the practicum. I put a message on Slack that might help you do that. There's an optional exercise at the end to go ahead and compare against observations error 5. So for documentation, the talk talk has links in it. So everything that you see that's underlined is a link to the actual help page. So here's the help page for a tool called NcRemap that we're going to start talking about. And here's one, NcClimo. This is what does the climatologies and the time series. So after this, if you run into questions, there's a longer cookbook of recipes and explanations on Confluence that you can go to. And okay, let's hop into regridding now. So the idea here is to visually demonstrate a couple of the types of grids that you'll be encountering in E3SM. You've seen the left-hand grid, that is the model spectral element grid. And then on the right, you have an MPAS ocean grid, and they're both unstructured. And here's how the terminology works. It was mentioned earlier that grids and meshes are essentially synonyms. The atmosphere people tend to say grid. The ocean people tend to say mesh. It's potato, potato. It's the same thing. The name of the grid for the atmosphere that on the low resolution mesh is NE30 PG2 in shorthand. Okay, you've talked about that already. The name of the grid in the ocean is a little bit longer, and so they can seem strange at first. They contain useful information, but this is the grid name. Let's distinguish that from the grid file. The grid file contains the geometry. It's a file, contains the geometry of the grid, the latitudes and longitudes and vertices of every single grid cell. So the underlined words, once again, are links. And so you'll find Confluence pages here that are publicly viewable with much more background information on grids and meshes in these two links. And here's a link to the server that serves the grid files, okay, for post-processing. So if you're looking for a grid like NE30 PG2 and you would like to compare it to something else, for example, error 5, and so you need to map between them, click on this link. It will take you to the web server that distributes the post-processing grids, and you can download it. Same thing for the ocean grid. Okay, so the grid file name actually contains the grid name in it, but it's much longer. So that's the file name. All right, so again, you got to get through the vocabulary before we start to work with it. So we've learned grids. What that means, it's just the name of the mesh that we assign to it. Land grids tend to run on things called RO5 or rectangular meshes, with the resolution being the inverse of the number you see. So this is a half-degree rectangular grid, and that's the default E3SM low resolution grid for the land. The files for those three meshes that I name up here are linked here. So those are the grid files containing the information you would need if you wanted to compare to an observational data set or a different ocean model than the E3SM is by default set up for in Zippy, which is other post-processing software that you'll see in a talk later on. In order to intercompare the outputs of a model with observations or other models, we're going to need to map grid cells for E3SM, usually the unstructured grid, to what we will call the analysis grid. The analysis grid means what grid are you going to do your mathematical analysis, compute your standard deviation of the seasonal cycle of temperature on? That's your analysis grid, okay? And typically, if you're intercomparing with other models or other data, you're going to use the most common coarsest mesh that they all sort of fit into. So you might have 1/2 degree data, 2 degree data, and 1 degree data, and you'll do your analysis for everything intercomparing on some maybe 1 degree or 2 degree grid, okay? So this is going to help you get that system going for your own science. And we have other tools, Zippy that I mentioned before, that will do this by default for E3SM on standard grids, usually a 1 degree by 1 degree grid. Yeah.
The gridding usually going from higher resolution to lower resolution?
Not necessarily sometimes. Often it's just taking it from the unstructured mesh that you saw, which is a number between 1 and 24,000, to a structured mesh, like a 1 degree by 1 degree lat-long grid of approximately the same resolution. But 1 degree in latitude and longitude at the equator is much different than the unstructured mesh at the poles, where the rectangular grid gets very fine, but the unstructured does not, okay? So, great question. So that kind of segues into the next term, which is the weight generation algorithm. If you want to preserve the value of the global integral of the field that you're regridding, you're going to want to use a conservative algorithm. So it conserves the product of the area times the value integrated globally, and that's called conservative. For some purposes, you actually want to do interpolation, and this often produces better maps of variables with properties like temperature, where you don't want to have the ocean contaminate the land or the land contaminate the ocean. So you're not actually going to weight those in a conservative way. You're gonna interpolate. And so there are conservative grids, with Tempest Remap AF being the preferred conservative grid for E3SM v3. Other examples of area averaging algorithms are here, or bilinear interpolation for interpolating data, not conserving it. It might give a better picture, okay? And those algorithms, again, Tempest Remap is the TR, bilin is the name of the algorithm. When you apply the algorithm to map one grid to another, you're actually generating weights that take each grid cell in the source domain and weight it by an appropriate fraction and put it in the destination grid, what we've called the analysis grid, okay? So where do you store those weights? That's in what we call the weight file or the map file, because that set of weights is uniquely arranged to take, usually conservatively or bilinearly, the data on the source grid to the destination grid that you're going to intercompare things on. So it's called a map file for short. Again, this map file is linked. It takes you to the map file server for post-processing, which is located at Argonne, I believe. And then we need one final step, a regridder. So the regridder is the software that applies the weights to data on the source grid and gives you the data on the destination grid. And there are multiple regridders out there. We're going to be using one called NcRemap. And again, that's linked. Okay, so you can either follow along or do this later if you wish. You can mouse these commands into your terminal window on Perlmutter. And we recommend doing all post-processing to be nice neighbors on compute nodes, not on the login nodes. So this first command is to open an interactive shell on the compute node, and you've probably already done that in Rob's exercise just previously. So today you would use the top command. On other days, if you have an E3SM account, you'd use this command. And then we recommend that you grab NCO by installing the E3SM unified environment through Conda. The easiest way to do that is to run this source command. That will give you NCO, that will give you Tempest Remap, that will give you, a Christmas talking full of software. So that's one way to do it. On your own laptop, you're not going to have probably E3SM unified. So you can just install NCO with Conda. Okay. The most common commands for NC Remap are shown here. With both NC Remap and NC Climo that we'll talk about next, you just type the command name and it will print all of its options for you so that you don't have to memorize this. We're going to start off with an existing map file and an input file in.nc, and we're going to write to an output file out.nc, and the map is going to transform it from the source grid to the destination grid. Okay, so that's the paradigm. Now, NC Remap also creates map files. So it decides what it's going to do based on what input parameters you give it and what you don't give it. So these are remapping. This command is inferring a grid file from a data file. Someone gives you an ERA5 data file or a MERA2 data file from NASA, and you don't know what grid it's on, so you infer it if it's rectangular. If it's an unstructured grid, you may have a hard time doing that. So I'll just skip over that. To generate the map file to take you from the source to the destination grid, the prototypical thing you do is you specify an algorithm with it -a source grid, which for the atmosphere is shown as an NE30PG2, a destination grid that might be 1 degree by 1 degree, for example, because that's the CMIP standard grid, 1 degree by 1 degree rectangular lat long, and then give it a map file name. The map file name says map, so you know what it's doing generally. Source grid to destination grid, and often you'll see a date after that. So putting it all together, and this will stay constant for any model component, atmosphere, land, sea ice, ocean, river, coupler. You're gonna regrid by giving it some model specific information, the MDL, a possible vertical grid, so to vertically regrid, horizontal grid, so to horizontally regrid. That's what we're going to be talking about today. The vertical example is extra credit for the practicum. If you want to try it, it's at the end of the talk. Input data, then output data. So for the simplest, taking E3SM raw output that you just looked at with NcVis on the unstructured grid, you want to put that on the CMIP grid, the 1 degree by 1 degree grid. For the model command, let's take some EAM data. So -p EAM, this tells, so there's some things going on in the background. If you don't give it the -p argument with a model name, it may or may not get all those things in the background done correctly. So it's best practice to always include the -p model name. And then some variables that you want to regrid. If you don't give it the variable argument, it regrids all the variables like you would expect it to. We're not going to do any vertical transformations. Here's the grid file name. Here's the input directory you just saw Paul access to get some sample data. So the input file is going to be the directory followed by one file name, and then you give it an output file. And boom, you run this command. Those are all environment variables, so the command should execute. All right, how much time do I have?
3 minutes.
Okay, great, great. The regrid command for Elm for the land model looks like this. You can see it starts with Elm and has Elm variable names. So now it's wrote. The form of the command stays the same. The regrid command for ocean, npass ocean, an ocean variable name. For sea ice, npass sea ice, a sea ice variable name. Okay, climatologies, same general setup, but you're going to be running NcClimo. Okay. Same general setup for NcClimo. Model specific information, some climatology information. It needs to construct the file names to input. Here it's going to be a 15-year climatology from the directory and the output that you have available to you. 15 times 12 files will be needed. So it automatically generates the file names for you when you give it the information of the start year, the end year, and the case name. And it will regrid as it does the climatology, giving you your output. Now you give it directory names. Put my native grid climatology here in my home directory /CLM and put the regridded data here in my home directory /regrid. Okay, so climatologies, 12-month seasonal files, annual averages. Here's the same thing for daily data, Elm, EAM, daily data. The command form changes for daily data and high frequency data because it's not predictable from the case name and the dates. So you just list the files and you pipe it to the command and you've given it the file so it doesn't need to create the file names. This is splitting the data into individual time series like you'd find in CMIP6. That's how we generate the CMIP6 data. After the workshop, if you want more information, you can click on any of these links. And during the tutorial, you can try the optional practicum exercise, which takes you through a full example with an ERA 5 data set and does vertical regridding as well as horizontal regridding. Thank you.
Next up will be Tom Bo. He's software engineer from Lawrence Livermore Lab, and he's a leading developer for xCDAT, which is the xArray based tool, Python tool. Yes.
My name is Tom Bo. As Jill said, I'm a software engineer at Lawrence Livermore. I am the lead developer of xCDAT, Xarray climate data analysis tools. In addition to xCDAT, I'll also do a little talk on E3SM Unified, Xarray, UXarray, and then xCDAT. So these are all Python-based tools, and Unified is the environment that encapsulates all these tools. So you will have them available in that environment. So just to give a briefer on Unified, so a few people already mentioned what Unified is, but I'll give a little bit more in depth of what it's about. Basically, it's a combination of a Conda and SPAC environment and includes all of these E3SM post-processing tools that allow you to do seamless data analysis, computations, and visualizations. It's developed and maintained by Xyler Osei Davis from LANL. And the software included in Unified include MPass analysis, Zstash, E3SM diagnostics, and all the other tools I just mentioned earlier, like Xarray. So some of you might be familiar with Xarray. It's a pretty popular tool nowadays. Basically, it's ND labeled arrays and datasets in Python. And the origin of it is it came from the Climate Corporation. So there's some climate science background there. It was originally released in May 2014 as open source, and then has been fiscally sponsored by NumFocus since 2018. So it's a pretty mature tool, and it has really good backing by the open source community. If you ever use NumPy, which is a standard, Python toolkit, it's heavily inspired by pandas as well. So if you do any type of Xarray based work, you'll notice that a lot of the syntax is very similar to these tools, and just basically working with Xarray should be kind of seamless if you know some Xarray and pandas or NumPy and pandas. So the difference with Xarray compared to raw NumPy is that it introduces labels. So what this allows you to do is basically do computations more seamlessly. So you don't have to worry about, let's say you're doing a subsetting on an axis. Usually you do like an indice, like 0, 1, 2, 3. You're gonna have to guess what axis you're working on. But Xarray allows you to choose the specific label. So time, there's a time coordinates, it's labeled time. You could just choose that and then do like a group by on it. And that makes the code really easy to read and reproducible. So that's one of the key points of Xarray. As far as key features, there's follow, indexing, selecting, grouping. It supports various file formats like NetCDF, Iris, OpenDAB, XAR, and many more. As I mentioned, it's inspired by pandas and it's based on NumPy, so there's interoperability. If there are scenarios where you need to, oh, sorry about that. So if there's any situations where you pretty much need to switch tools, you can easily just extract the underlying array in an Xarray object and then perform that analysis using a different toolkit. As I mentioned, there is some history with climate science in Xarray, but they're trying to develop it in a way where it's general purpose, so it doesn't apply to domain-specific use cases. However, there are a large ecosystem of Xarray extensions, which I will mention in the following slides, and this helps you, solve those use case specific needs. One of them is UXarray. So basically, it's an extension of Xarray, but it supports unstructured grids. And it's a project that's funded by Project Rygen and SEATS, which are NCAR and DOE projects. And basically the goal of UXarray is to address the geosciences community's need for standard analysis techniques to be able to be applied on unstructured grids. And basically we're trying to follow standard conventions like UGrid, MPAS, Script, E3SM, and Exodus. And on the technical side, it provides standard Xarray style functionality for reading and directly operating on unstructured grids. So Xarray in itself, you can open up these unstructured grids, but those objects don't, those underlying objects don't have any unstructured grid functionality. So it doesn't recognize like grid topologies and things like that. And UXarray is able to fill that gap. So I won't really go too deep on the core data structures, but these are some that you might see if you read through the technical documentation. There's a grid object, which is basically the unstructured grid that houses, specific grid-specific methods and topology variables. There's the UX dataset, which inherits the Xarray dataset class and provides the unstructured grid methods and attributes on top of the Xarray dataset class. There's the UX data array, which is similar. It inherits from the the Xarray data array class and provides the unstructured grid methods and attributes. And both of the UX dataset and UX data array object have grid objects attached to them, so they're kind of in sync. It allows you to do analysis on both simultaneously. So you could also extract it separately, but they're also kind of combined together. As far as intended functionality, so this is pulled from the documentation. Basically on the grid side, the intended functionality for that is it allows you to read, write, UGrid, all those standard conventions like script, E3SM, do calculations of face areas, triangular decompositions, calculation of super meshes. And then on the data array side, there's regrading of data between unstructured grids. So you could go from one unstructured grid to a different unstructured grid through UXarray. And then there's also things like application of calculus operations, global and regional integration of fields, so on and so forth. And if you're interested, there's, the documentation lists all the intended functionality. And this is just some example code in Python with just opening up an unstructured grid data set with a grid path and a data path and using UXarray's open data set. And then we're visualizing the grid topology, performing some total face area calculations, and then visualizing the data as polygons. So you can just see the resulting plots from the code here. So the grid topology is on top, and then the data itself as polygons is on the bottom. And then, so basically I was giving you an introduction to the unstructured grid analysis side. Now we're shifting over to the structured grids. And this is where xCDAT comes into play. It's an extension of Xarray as well. And it's a collaboration between E3SM, PCMDI, and SEATS project. The goal of xCDAT is to provide features and utilities that allow you to streamline climate data analysis, make it really easy, simple, and robust. As far as production usage, it's being implemented in various other packages like E3SM Diagnostics, PCM Diametrics package, and it's also included in E3SM Unified. As I mentioned, these are some of the features that xCDAT provides so that it allows you to streamline your computations and analysis code. So there are things like, sorry for all the VPN thing popping up, but pretty much it provides things like geospatial weighted averaging, temporal averaging, climatologies, departures. You could do this in pure Xarray, but xCDAT encapsulates it so that you could easily reproduce that feature and apply it to different, scenarios. So let's say you need to group by a different frequency instead of month, you could easily do that in a day. And there's an API where you just configure it. So you don't need to recode things over and over just for that specific, those specific cases. Including that, there's also robust handling of CF metadata. So that's a convention, it's a CF metadata convention. And what this allows xCDAT to do is interpret those attributes and perform robust calculations by interpreting it and mapping it to the correct, dimensions, axes and whatnot to calculate things like weights, generate bounds for coordinates, so that your computations are, robust and, accurate. There's also horizontal structured regrading, vertical structured regrading. Those are extensions of other packages, but basically what xCDAT does is it preserves the metadata and also generates bounds if they're missing, so that when you have the output, it's in a state where it's that it's high quality. So when you do the analysis, it has all the information you need to do downstream calculations and operations on it. So this might be really small, but the idea here is just to compare the number of lines of code that you need to implement global mean monthly anomalies in Xarray and compare it to xCDAT. So basically in Xarray, you have to do a lot of verbose syntax in order to achieve the same functionality as you would in xCDAT. So it takes around, let's say 32 lines with the imports. On the xCDAT side, it only takes 17, 18. And there, if you kind of look around 23 to 31, there's a section of code here where it's a lot of verbosity as far as generating weights, doing the sums and the divisions. And that you could easily mess that up if you forget to switch the label or group by a different frequency. So instead of month, you accidentally do a year, it could really mess things up here. As far as xCDAT, you could see that 7 line of code was encapsulated into 1 line of code at the very end on line 17. And all you need to do is run that API on the dataset object, pass in the data variable that you want to operate on, and then the frequency. So we're doing year right here. So that's all it takes to do the same thing in Xarray, but in xCDAT. So I kind of went through that pretty quick, but I'll give you a quick recap instead if things flew past your head. E3SM Unified, combination of a Conda and SPAC environment, includes all those major post-processing tools. Xarray, open source project, provides labels on top of raw NumPy-like arrays. And it makes the experience of development much more streamlined and intuitive compared to just using raw NumPy. UXarray, extension of Xarray, but for unstructured grid analysis. And then xCDAT is geared towards structured grid analysis, but provides functionalities that streamlines the actual computation and the analysis portion. So, and here's some resources, documentation. You can just find this on Google. It's basically all on Read the Docs. Besides the unified documentation, it's on the official E3SM website. So yeah, so any questions before I go over like the practicum exercise that I provided? Cool, so I'll go ahead. Yeah, that's good. I mean, it either flew past your head or I just said everything, smoothly. So as far as the practicum exercise, we're gonna work on Jupyter Hub. There's a nurse portal that you log into, provides a whole UI interface. We have 2 notebooks that we're gonna run through, and one is on UXarray and the other is in NCL with xCDAT. So the first one, general introduction to UXarray, basic computations, visualizations. Second one, we're gonna do some remapping using NCL, and then computations and visualizations using xCDAT and Matplotlib. So I provided all the instructions on the Slack, and And also on the agenda, if you go to like my portion on the table, you'll see these steps here. First, you're gonna need to log into the Jupyter Hub and then clone the repo and then just find the notebooks and everything should be set up. I'll also do a quick little demo of that just in case you're not familiar with this process. So if you click this NERSC link here, you'll be sent to this website where you need to log in. So it's your NERSC credentials. I'm trying to make this bigger. So you have to sign in with your NERSC credentials here. It's going to ask you for a username and password as well as the MFA, the multi-factor authentication key. So once you log in, you're going to click on under login node, you're going to click server. And it will load up into the Jupyter Hub. So if you're familiar with this, it'll be really easy for you. But just for anybody who's never used any like Jupyter type environment, this is hopefully this helps. So once you're in the Jupyter UI, you want to click New Terminal. And we're going to run that git clone command to get the repo here. And it will clone to your home directory. It will pop up right here. There are 2 notebooks under demos, E3SM workshop. Just open them right here. And you will, if you open it up and it pops up this kernel selection, just ignore it, just click select. We're going to use the unified kernel. We're going to set that up and you could, get running after that. So hopefully that's pretty clear. Let me know if you have any questions. We have TAs here to help as well. Steve is one of them in the back. But yeah, just raise your hand if you need any help. So thank you, everybody.
Great. We will, during the tutorial during the week, we will go back to the run script again and again. And today we just say because the NERSC very supportive for us, we have a relatively sizable chunk node reserved for us until midnight. So you make use of them, submit the job for non-simulation until midnight. So the script is here. If you don't have the link, so that we no. This one, some of the link not working. This is the link. The browser here. So you happen to be using Firefox. The script in there not working for me, Firefox. But that's okay. So we'll just say roll the page back and forth. So we're going here for the preparation for the non-simulation. Yeah, if you are not using Firefox and you'll be able to copy the link, like say we previously have the run script for 1 day. But the first thing I want everybody to, like say, while on browser, also open a terminal from the next terminal. See, enter this directory. That would be the previous one. You create a case for 1 day, enter this directory and check this command. See if you have the build directory and also have an E3SM.exe executable. If you have that one, that means your 1 day run was successful. Yeah, stay on this page. And I want to see if for any of you already entered this directory and see you have this E3SM.exe, can you raise hand and see how many successfully do that? Oh, we have, congratulations, we have over 10 people, right? But many of you probably already know how to run it, you didn't try. But if you have it or not have it, the next step is going to be different. But just to take note there. And the next step would be, if you have this script, you copy this script to one script, which just name it as a 1 year simulation. under your E3SM underscore script directory. So we will use this file data structure. Tomorrow we'll also use it and then check some of the simulation. And after you copy that one, so you can, if you are comfortable to edit in this Unix environment, you can do this. If you are not familiar with the Unix editing, try the alternative one. So if you do this one, basically it will be after you copy this run script, so we'll change this 3 line. In this script, one is this read only, that was the run set to run for 1 day. But you comment that one out, put the pound sign at the beginning, and then uncomment this line is on line 67. That changed to a production run. And with the production run, for those of you, you have a successful run, you already have a executable, then you don't need to rebuild it because rebuild takes 10 minutes, about 10 minutes, then can reuse it. But if you haven't tried that and don't see an executable there, don't change it. If you change to true to false, it will give you an error and you will need to go back to reset it. Or another way, if you don't edit, just copy over this script that's already modified. However, do case build was set to true, so still not ideal. If you're using this one, if you didn't have a successful run, you need to change the do case build at 9.1.11 to true, then it will build. So I can go back to this server setting here. Yeah, some of the active link not work for me, so I go back here. There will be this part of the from the 9. Yeah, there will be these several lines. The 9 here, Chris described earlier, the run is a two nodes for 1 day. So it's comment out this line, and then uncomment this line, that means to get the production run. And with the production run, the P layout we prescribed, this one is used a node. So the format is here, and this parameter going to be used in the sim-based command. That's to use a node. And for 1 year simulation with a node going to take about 5.5 hours. So we set work clock about 6 hours and 30. So specify here 6 hours, almost close to midnight. And we only have a request reserve node, only 2 nodes per person. So if to submit a nodes, only about 15, the early goer will be able to get the job start right away, and the other in the queue. And by the midnight, some of the job will be completed, some probably stop in the middle, and some probably not able to get started and sitting in the queue. And tomorrow we get a chance to check on that one, whose job is still there on the day 1 reservation. So this is the setting here. Tomorrow and the day after, we will continue to walk through this kind of different setting in the run script. Then after this one all ready, then is the end of this page. Directly copy over this run script. Or either you modify it or copy this run script, then just run from your E3SM case script directory and just simply copy this command over and submit the job. Considering if maybe it's still waiting, you can put like say in the background, put a pound sign at the end of the command. Or maybe even better, put the no hub and then pound sign at the end, and then you can immediately shut down the computer, everything sent to the background. And later, if you have a chance, you can enter this directory and look at the case structure. Where is the build directory? Where is the case? Where is the run directory? How the output looks like. If you are not familiar with that one, tomorrow will continue to go over those. So these are basically, yeah, that's all. So remember for this one, if you want to submit, if you already have set this one to false work for you, you probably like say within 1 minute is submit the job to the background, to the batch. If you didn't run successfully earlier, and this one build is true, then you better put a pound sign send to the background. Otherwise, it will sit there for about 10 minutes to finish the compilation.